So as you can tell here, given that y equals x squared is not is a function, but its inverse is clearly not a function, right? This is because this will not pass the vertical line test. But sometimes what we can do is actually restrict the domain of the original function in order that the inverse is also a function. So the reason why this is not a function is because when this graph, y equals x squared, is reflected in that line y equals x, it has two parts to it. This one part, the positive, and this negative part. So we want to get rid of that if we can to make the inverse also a function. And what we can do then is restrict the domain here by saying that, well, if we only use this positive part of that function, so the positive domain, right, like down here, then when we reflect that, we will end up actually getting a function as the inverse, right? So it'll give us this inverse piece, and that's sometimes useful if we want to solve the other way around or undo that original function, right? So the idea here is that if we're looking at the domain of the original function, x is an element of real numbers, and the range is that original function, right? So if we have the original function, domain, and range, then the inverse is not going to be a function in this case. Okay? But what we can do is restrict that domain. So instead, if we say that for y is equal to x squared, we have a domain of x is an element of real numbers, but x is greater than or equal to 0, and then the same thing with the y. The range would also be at y is greater than or equal to 0, but we're not really restricting that. It's just based on the function. Then what ends up happening is when we do the inverse of that, okay, we end up getting a function as well. Okay, and that's actually sometimes very useful. Okay, so it is possible to restrict the domain so that when you do the inverse, it is also a function. So let's look at an example here. So this example here, again, try not to look too far ahead into what's below, but if we have this function here, that is the connection of these 6 points, then basically what we can do is we can find the domain and range of that function, and then we can also find the inverse of that function. So when we look at this function, we can basically say it's made up of these 6 points, right, that are right here. Okay, but let's look at the question first. Question is, sketch the inverse of the function, and then state with justification whether its inverse is a function. State the domain and range of both the function and its inverse. So it shouldn't be too difficult here. We can look at this and say, all right, well, in terms of the x values we're using, right, it's going to go from -4 all the way to +3, and that would be inclusive. So when we look at that, that domain is going to be from -4 to +3. Okay, that should be pretty straightforward. The range is going to be from -4 up to +5. So that's why we have this value as our range, right? The -4 all the way up to +5, with y being an element of real numbers. So when we do the inverse of that, again, the inverse is just going to be the exact opposite. So what we had for the range now goes over to the domain. What we had for the domain now goes over to the range. Okay, so that'll be our new blue. I'm going to just color it blue here. So again, from -4 to 5, and then from -4 to 3. Now you can do that right away, or you can graph those points right away. So remember, if you're looking at mapping these points, we're taking x, y, and we're mapping them to y, x. Okay? So this point here is an invariant point. This point down here, I'm sorry about that. Don't know what happened there. This point down here is also an invariant point. Okay? So they do not move. So -4 stays the same. 3 stays the same. So we can leave those there. Sorry. So then you can basically move all of those points over, right? You get the idea here. Shouldn't be too tricky, and I'm going to just erase all those. Okay, so then the question is this other one a function or not? Is the inverse a function or not? And if you look at just the points, let's look and see all the x values of the image. And then you got -4, 4, 5, 3, 4, and 3. So right here, we should look at this and say, whoa, there's something wrong here. We've got -4. We've got +4 giving a y value of -3, and we've got +4 giving a y value of 1, right? So that's this point here and this point here. And those 2 points obviously make this not pass the vertical line test. But really, you just have the same x value producing more than one y value. So that definitely will not be a function. But you don't even need to do it that way. You could just look at this point, or at this inverse, and say, okay, well, if I draw the line through here, it passes this, it crosses this graph once, twice, 3 times, 4 times, which clearly does not pass the vertical line test. Okay? So this function is clearly not, the inverse of this function is clearly not a function. All right, so we're going to look at this question now. It says algebraically determine the equation of the inverse of f at x equals 3x minus 2, and then graph it and its inverse. Okay, so we're going to look at the steps for this. And again, we did these in class. Doesn't matter which order you do them in, but this is the one we're going to follow. So we're going to replace f at x with y if you need to. Remember, we showed in class that you don't necessarily have to replace f at x with y, but you can. Okay, and then for the inverse, you're going to interchange x and y in the equation, or x and f at x in the equation, and then you're going to rewrite the new equation in terms of x, and then state any variable restrictions. Okay, so if we look at this equation right here, we're starting with f at x equals 3x minus 2. Okay, then we can start by substituting f at x with y, so we can say, well, y equals 3x minus 2. If you're wondering, I'm just following along right here. Then we're now going to interchange x and y. So I'm going to write actually the exact same thing, but I'm going to interchange my x and y. So now x is here and y is there. And now I'm going to isolate for y. So when I do that, I isolate for y, I get y equals x plus 2 over 3. Okay, there's no restrictions there at all. So now what we're going to do is we interchange y here for f inverse at x. Okay, so that's like f inverse at x equals x plus 2 over 3, which then when you're graphing these two things, this is just the equation of a line, so you start down here at -2, and then you're going to go up 3 over 1, up 3 over 1, and that's why you get that line like we do there. The inverse of that is just going to be reflected in the other line, in the line y equals x. Or you could look at this saying it starts at a b value of 2/3 and then goes up 2 over 3, up 2 over 3, etc. Okay, so that's basically how we find the inverse. So remember, if you need to, you can replace f at x with y. Then you're going to interchange x and y, write the new equation in terms of x, which means y equals something with x as the variable, and then state any variable restrictions. Okay, and then remember, actually one thing that we're not showing in here is that then you also replace y with f at x, inverse. And that clearly doesn't look like an inverse. Okay, so once you have that, you're going to say, well, y is the same thing as f inverse at x.